Hello, welcome. I am Reji Kumar, Assistant Professor, Department of Mathematics, NSS College, Chatala, Kerala, India. I am going to give a presentation on mathematical foundations of information processing. I would like to express my sincere gratitude to the organizers of the second International Conference on Artificial Intelligence and Advanced Manufacturing 2020 happening in Shanghai, China. These are the content of the presentation. First, introduction, then comparisons and relations, next some results and references. What is consciousness? One of the major challenges that the scientists face today is to develop a model that can explain human consciousness very well. Consciousness is the end result of all processes taking place in our brain. A major share of the mental processes involve the manipulations of various kinds of information received from the outer world and the inner world or mind. Information includes all kinds of data received by our mind, both from the outer world and from the inner self. Next, we are going to discuss an axiomatic approach to the problem of representation of consciousness. Every theory is built on a set of axioms and definitions. An axiom is a self-evident or universally recognized truth. It's a self-evident principle that is accepted as true without proof. It's the basis of all arguments in a theory. In non-mathematical contexts, a statement is accepted true only if there is no counterexample against that statement. But in mathematics, true statements are logically derived from a set of axioms. So, axioms are mathematical statements that serve as the starting point from which other statements are logically derived. A mathematical theory of consciousness is presented by Kumar. This theory is built on the main assumption that models are the building blocks of consciousness. A model is a primary representation. It's a representation, or it's a preliminary representation of something which carries some character or property of the objects which is represented by it. Sometimes the models are expected to have just a correspondence with the object. Model-based approach to the study of consciousness is not a new thing. It was adopted by some researchers in 1943. A computational scheme of a mental model was set forth by Craig, which was then extensively elaborated by Johnson Laird. Later, this idea was used by Ito to describe the processes in cerebellum related to movement and thought. Following their path, Vanderwert tried to explain how working memory and cognitive modeling functions of the cerebellum contribute to discoveries in mathematics. Models are the fundamental units of consciousness. Models can represent reality. Some models can be expressed in terms of submodels. A collection of models can make a new model. Relationship among models is a new model. These are the model axioms, and based on these model axioms, a mathematical theory of consciousness is developed. We have some special kind of models to discuss. We use the null model and the concept of null model and universal model in our study, and this is to make the theory meaningful, and also it makes it mathematical. We denote the collection of all models that constitute a consciousness of an individual by the individual, suppose the individual is X by Cx, and any model in the consciousness can be denoted by M. The collection of all models which generate a model M is denoted by MC if some models M1, M2, etc. to Mn, or suppose these are the models, are the submodels of a model M, then we write M of MC is equal to M1, M2, etc. to Mn in set notation. If Mi is a submodel of the model M, then we denote it by Mi less than or equal to M. Also, if Mi is a member of the class of models, then it is denoted by Mi is an element of MC. Every model is a submodel of some model. So M is an element of MC. Two collections of models MC1 and MC2 are equal if all models in one collection are in the other, and if it happens vice versa. It is denoted by MC1 equal to MC2. Here we define the equality of models. A collection of models that represent an object or reality or imagination, say O be that reality. Suppose O be the reality, and that model is then denoted by a tag associated with it. That's the tag O, M subscript O. Two collections are equivalent if they have at least one submodel in common. Here we define the equivalence of two collections of models. We compare two collections of models and we say that those two models are equivalent if there exists at least one submodel which is common in both collections. If there exist two collections of submodels, here the focus is on submodels of collections of submodels. If there exist two collections of submodels of the same model, say MC1 and MC2, we call the collections equivalent. So here the equivalence is defined based on representation. Okay, and thus in the first case it was the presence of some submodel in the collection that make equivalence. But here in the second case it is some kind of attachment of the collection of submodels to some reality which make those collection equivalent. Hence we can see that there exist two kinds of equivalence. So two collections of submodels of the same model which represent a reality are equivalent. Thus in the sense, in the sense of the second point presented here, we can say that two collections of submodels which represent the same reality and they are treated equivalent, because it is assumed that a collection of submodels which represent a reality contains the whole model representing the reality. So this is the logical basis for the second argument. Okay. Thus the equivalence here comes from the equivalence that we have defined in the first case. Two models are submodel equivalent. So we have the first kind of equivalent, submodel equivalent, if there exists some common submodel in their respective collections. And we define the other type of equivalence which we call the representation equivalence, that was discussed in the as the second point in the previous slide. Two models M and N are representation equivalent if they represent the same object or reality. Representation can be classified into two. One representation is by establishing an association or link between the model and the thing represented by that model. This method is very simple and static. But the second method is by comparison and matching. It's complex and dynamic. Once the link is established, the first kind of representation remain unchanged. On the other hand, the second type demands continuous improvement or correction in the representation. There are two relations which are particularly important in our study. So here in this slide we are going to discuss the relations defined on collections of models. First relation is the submodel relation, denoted by RM, R subscript M, and we denote suppose there are two models M1 and M2 that we compare, and we say that these models are related with each other using the submodel relation if and only if there exists a model M such that M less than or equal to M1 and M less than or equal to M2. But now we are going to define the supermodel relation, which will be denoted by M superscript M with respect to the presence of a model M, that will be defined as M1 R superscript M of M2 if and only if there exists a model M such that M1 less than or equal to M and M2 less than or equal to M. That means the first model and second model are both the submodels of the same model M. Then we say that they are supermodel. They are related using the supermodel M. So it's a kind of we can say that it's a supermodel relation. The following result, we have some results which are established, which are derived from the concepts of relation, equivalence, and similarity, and the submodel and supermodel relations that we are going to discuss in the coming slides. First theorem says that the submodel relation and supermodel relations are equivalence relations. We can prove this. Second theorem says that if M1 is a submodel of M2, then we have M2C is a subset or equivalent set of R M1C. Next theorem, for any two models M1 and M2, we say that M1 equal to M2 if and only if we can say that M1 equal to M2. That means the two models are equal if and only if M1 less than or equal to M2 and M2 less than or equal to M1. Theorem 4, for any two collections of models are M1C and RM2C. RM1C equal to RM2C, RM1C equal to RM2C if and only if M1 equal to M2. The models M1 and M2 are different if and only if there exists a model N such that N less than or equal to M1 and N not less than or equal to M2, or N less than or equal to M2 and N not less than or equal to M1. Similarity and equality are two very general models which result from comparison. In the light of the discussion so far, it is clear that two models M1 and M2 are similar if and only if there exists a model M such that M less than or equal to M1 and M less than or equal to M2. Equality, on the other hand, demands similarity with respect to each and every submodel. Similarity is quite simple and that can be verified. But equality is extremely difficult by nature. It's very difficult and it's very difficult to verify. It's because we have to take into account all submodels belonging to a particular model. So taking one by one, we have to consider all. We have to compare all submodel of a given model with the submodels of some other model, to say that whether the first model is equal to second model, and hence it becomes a very difficult task when we think about the situation in terms of combinatorial complexity. And finally, we have the main references used in this discussion are given here. And the first four belong to the literature, the previous developments in historical developments in the field of mathematical modeling of consciousness. And the fifth one, it belongs to the axiomatic approach, the work presented in this paper, axiomatic and mathematical approach to the problem of consciousness, was presented in this paper. This was a project report submitted to DRDO after completing the project gathered by them. Next is next one. It's a publication on the topic on classification of models, and last one is a work published by Van der Waart, how working memory and cognitive modeling functions of cerebellum contribute to discoveries in mathematics, and that explains the consciousness based link with the discoveries in mathematics. Okay, thank you. Once again, I would like to thank the organizers for giving me this opportunity to make this make the presentation in this conference. Thank you all.